Hello and welcome to our project presentation, Stereo Disparity Map Acceleration with HLS. If you enjoy this video, please like and subscribe. Stereo disparity matching is the process of finding the depth information of objects within a 3D space using multiple images of the same objects but taken at different angles. In our stereo mapping scheme, there are two cameras. The two cameras are placed in parallel along the x-axis and produce two different images of different angles. We use stereo matching algorithm to estimate how far away objects in the images are from the camera.
In this problem, we are trying to find the disparity value for each pixel in the left image. Because of the setup of stereo cameras, a pixel in the left image should appear in the right image on the same row, but to the left. The diagram better illustrates this relationship. The disparity value is the difference in horizontal distance between the pixels positioned in the left and right images. The further away an object is to the camera, the smaller the disparity value. Thus, from the disparity values of each pixel, we can reconstruct a depth map. Here we are showing an animated example. To find the disparity value of one pixel, we look at not only the pixels, but also the pixels surrounding it, and that's called a patch. Pixels that are out of bounding a patch are padded with zeros. We use the sum of difference square to evaluate how well the two patches match. In this example, the sum of difference is calculated to be 59. So we record the current minimum difference to be 59 and the disparity value to be 5. Moving on to the next patch on the right image, going through the same calculation, the sum of difference becomes 27 in this case, meaning this patch is a better match than the previous patch. Therefore, the minimum difference is updated to be 27 and the disparity is updated to be 4. After finding the disparity values, the results are often noisy, so we use a Gaussian filter to smooth the results. This is a simple convolution operation. And this is the pseudocode for CPU. There are quite a few nested for loops inside, indicating potentials for parallel computing on FPGA. This is the disparity map produced by the baseline algorithm. Further objects have smaller disparity values, so appear darker on the picture. Closer objects have larger disparities, so they appear to be lighter. In this disparity map, we can identify the lamp that is the closest, and then the statue and the table behind.
When porting the CPU serial code to the hardware, the first thing we realize is that there's not enough storage on the Z board to hold all 6 input images. We have to stream in the pixels to local image buffers to allow further processing. Thus, we decided to reconstruct our code to implement tiling. The input image buffers each has patch size of rows, where patch size is the height of the patch the find_disk function operates on. The disparity buffer holds the computation results of the find_disk function and has filter size of rows that the smooth function can apply Gaussian filter for. This way, we minimize the memory overhead of our kernel. Each iteration in the stereo kernel outer loop, a new row from each input image gets streamed into our image buffer. The find_disk function then processes the new patches, which is one row below the previous patch it works on, and generates a new row of disparity value to put in the disparity buffer. The smooth function performs filtering with the newly produced row and streams the output to the host code. This implementation minimizes the amount of data movement between local buffers and the host stream and allows a new row of output to be generated in each iteration. With the established stereo kernel properly operating on the Z board, the first optimization we did is unrolling and pipelining the loops with HLS pragmas. From the pseudocode on the screen, we can observe that all of the inner loops have fixed iteration boundaries that are reasonable to unroll. The limb loop in the red, however, can range from 0 to a max disp of 600 for our input image. Thus, we decided to pipeline the loop, which gives us significant performance improvement. The image and disparity buffers are partitioned by rows to give the most optimal initial interval for the pipelining scheme, which is 2 for our algorithm. The next optimization technique we have is manual unrolling. This is due to the fact that unrolling with HLS pragma requires further partitioning of the buffers by columns, which will introduce suboptimal array access and decreases our performance. Manual unrolling not only avoids the issue, but also reduces the amount of access we need for the image buffer. To find disparity for a pixel at index I in the left image, all of the patches with index less than I in the right image need to be compared to. The red patch, for example, requires access to all of the right pixels on the right image, and similarly for the blue patch. And from the animation, we can observe that all of the overlapping pixels between the two can be reused with manual unrolling to reduce the latency. This is a demonstration of how manual unrolling is performed. An unrolled patch of 3x4 is obtained from the left image buffer, which represents two patches. Each iteration reading patches on the right image. The pixel values are used to calculate the disparity for both indexes on the left image, except the non-overlapping loops. So for the first iteration, the patch on the right image is only compared to the first patch on the left. And as we move forward to obtain the further patches on the right image, it will be able to be used to perform the computation on both of the patches on the left, which significantly reduces the image buffer access overhead introduced in our algorithm.
Another idea that exploits the data reuse is to implement a buffer storing disparity history. Previously, from the pipelining stage, we already partitioned the buffer into different rows. However, there's still a memory bottleneck for accessing the columns, since our patch size is greater than 2, which is the number of read-write ports for BRAM. Thus, even when we unroll the two inner loops across the patch size, we cannot achieve an II of 1. The idea is that for each comparison in the row, there's a significant overlap between the results from the pixel and the pixel to its immediate right. Thus, we maintain an array of max D elements which stores the sum of square differences between patches with patch size rows and patch size -1 columns for each disparity value. For each iteration, we read and calculate the sum of square differences for the rightmost column of the patch and add that result to the one in the buffer, and use that collective sum to update the min disparity variables. Then we read out the leftmost column of the patch, calculate that sum of square differences, and subtract it from the total sum to prepare the value for the next iteration. So for each iteration, we only have 2 reads, and we can reduce the initiation interval to 1. Unfortunately, while this synthesized with an estimated latency of 2.243 seconds, just shy of 2x speedup from the pipeline optimization, we were unable to compile this bit stream. Lastly, we tried to reformat our code to allow for functional pipelining across the read, find disparity, and smoothing functions. We did this by adding in intermediate buffers with the capacity for 1 row that the producers would update and the consumers would read. Even with these changes, we were unable to get this to conform to the correct data flow structure and did not pursue this optimization further due to the find disparity function having a much longer latency than the other functions. Here we have the evaluation. We can see that the HLS baseline was almost 2 times slower than the software baseline, which shows that optimal HLS code is often not the same as the optimal software. Furthermore, we were able to see a 12x speedup just from pipelining the limit loop and could further reduce the expected execution time by almost 2 times with manual unrolling. The manual unrolling is done based on knowledge of the specific parameters that we chose, which we can see that improve the performance but at the expense of flexibility and modularization. Despite this estimation, in reality we see very little reduction in the measured runtime. We confirmed with a dummy module that simply reads the pixels and writes zeros to the output that the I/O runtime is comparable to the runtime of our kernel, which indicates that the bottleneck is in data transfer. This is ultimately the limit to our performance. Overall, we also found that as we increase the complexity of our optimizations, our resource utilization also increased. And lastly, we have a demo of our accelerator running on the Z board. This is the end of our presentation.